Have you ever wondered why light has energy but no mass? To answer this, we need to rethink what we understand about mass. If you've ever taken a science class, you've likely heard mass defined as the amount of stuff in an object. But this definition is a bit simplistic and doesn't totally capture the full story. In reality, mass is about energy, specifically energy at rest. Now you're probably wondering, what does energy at rest even mean? Well, let's dive into that. Imagine you're sitting on a bench resting. Even though you're not moving, there's a whole lot of activity going on inside you. Cells are dividing, blood is circulating, neurons are firing. All these processes involve energy. This energy, even when you're sitting still, is what we call rest energy. But how does rest energy relate to mass? That's where Einstein's famous equation E=mc² comes in. E stands for energy, m for mass, and c² is the speed of light squared, a really big number. This equation tells us that mass and energy are essentially two sides of the same coin, and it's not just any energy we're talking about here, it's rest energy. So if we rearrange the equation a bit, we can express mass as rest energy divided by the speed of light squared. This gives us a new way to think about mass, not just as the amount of stuff in an object, but as the energy that object has when it's not in motion. This concept of mass as rest energy helps us understand why light, which is always in motion and never at rest, is said to have no mass. But we'll get into that in more detail later. So, mass is not just about the amount of stuff in an object, it's about the energy at rest. This realization sets the stage for us to delve deeper into the fascinating world of physics and challenge our understanding of concepts we thought we knew. But what about moving objects, Einstein? You might ask. Well, let's take a journey into the world of moving objects to understand this better. Picture this. You're compressing a spring. You're putting in effort, you're using energy. But the mass of the spring doesn't change, does it? The energy you put in is stored as potential energy, not rest energy. So while the total energy of the spring increases, its rest energy, and therefore its mass, remains the same. Now, imagine you're heating up a cold cup of coffee. The coffee's molecules are moving faster, they're buzzing with kinetic energy. But again, the mass of the coffee doesn't change. The kinetic energy is not part of the rest energy. The coffee's mass, its rest energy divided by the speed of light squared, stays the same. Let's take another scenario. A tennis ball flying through the air. The ball has kinetic energy because it's moving, but does this mean it's heavier than when it was sitting still? No. The ball's rest energy, its mass, doesn't change just because it's moving. These examples illustrate a crucial point. The rest energy of an object, and therefore its mass, does not depend on the object's motion or on any external energy we put into it. This is what we mean when we say that mass is the amount of rest energy an object has. So when we talk about an object's mass, we don't mean its total energy, we mean its rest energy. And it's this rest energy that E=mc² refers to. No matter how fast an object is moving, no matter how much potential or kinetic energy it has, its rest energy, and therefore its mass, stays the same. Even for moving objects, it's the rest energy that matters when we talk about mass. Now, let's shine some light on photons. When we apply the principles of mass and energy to these particles of light, we run into a fascinating conundrum. Photons are always on the move, traveling at the speed of light, which makes the concept of rest energy a bit of a head-scratcher. How can we calculate the rest energy of something that is never at rest? Here's where an alternative definition of mass comes into play. What if we considered mass as the total energy divided by the speed of light squared? This would give us the concept of moving mass, which might seem like a neat solution to our photon puzzle. But hold on to your lab coats because Einstein has something to say about this. Einstein argues that this definition of mass, although intriguing, brings about its own set of complexities and contradictions. In the realm of light speed, we're dealing with the very fabric of space and time. Here, our everyday notions of mass and energy start to blur, and defining mass becomes a slippery task. It's like trying to pin down a shadow. It keeps shifting and eluding our grasp. So, while the idea of moving mass might be tempting, it's not a one-size-fits-all solution. In the world of physics, things are rarely that simple. It seems defining mass in the realm of light speed can get quite tricky. So, where does this leave us with our original question? We've journeyed through the realms of rest energy, explored scenarios of springs, coffee, and tennis balls, and even attempted to unravel the mystery of the massless photon. Each venture has illuminated a different facet of the elusive relationship between mass and energy. The cornerstone of our understanding lies in Einstein's equation, E equals mc², which suggests that mass is essentially the energy of an object at rest. But what about photons, those particles of light that are always on the move, never at rest? Here's where things get interesting. Imagine, if you will, a universe where photons travel slightly slower than the speed of causality. In this alternate reality, photons could have a rest energy and hence a mass. It's a tantalizing thought, isn't it? However, we must tread carefully. This notion introduces a host of complexities and contradictions. It challenges the very definition of mass and prompts us to reconsider our understanding of energy. In the end, Einstein concludes, objects traveling at speeds less than the speed of causality should be massive, while those traveling at the speed of causality, like photons, should be considered massless. This conclusion may not answer all our questions, but it certainly gives us a fascinating perspective on the intricate dance between mass and energy, a dance that continues to captivate scientists and thinkers across the world.